Well, good afternoon. This is supposed to be Math 238, differential equations. It's 2:37, which is 7 minutes late getting started. I've been waiting for someone to show up. No one has yet, so we'll go on and get started from here. Just a couple of announcements. Nothing too critical or too close, but just things coming up. First, I've announced to you before about Alabama A&M having the North scholarships. You got the email. If you get the email, you can link to the site that's listed here, find out all the details, see if you're interested. If you are, see what is required to apply and get on the application process. So that's up to you. Now, number two. By the way, I need to pause just a minute here and update my roll sheet. All right, sorry about that. Secondly is stuff that I've got coming up for the next 3 Fridays. This is sort of a pain in the neck. This Friday, coming up, March 1st, I have a dermatology appointment Friday morning at 9:15. Now, what I don't know about this is whether I'll go to Birmingham West Campus before the appointment or not. If it's so, I would get there, a little before 8, but have to leave by 8:45 to drive back to Birmingham, near UAB, and go to my appointment. And if it's 9:15, going to maybe 10:15, then driving back, maybe get back to campus by 10:45, and then I'll be there till afternoon anyway. So I don't know whether I'll do the first part or not, especially if there's anything to be done on the campus. I might have to go, but if not, I can actually get a lot more done saving those 2 30-minute segments of driving and working at home or in the doctor's office, which is probably what I'd wind up doing for part of it anyway, and get more done than I would driving back and forth between campuses. So I've got to check with my boss probably this afternoon to see what he wants me to do. But then in the later part, the 10, I'm just guessing 10:45 to 12, I'll be there sometime. I don't know what time the appointment will get over and what time I can get away and there, but we'll get there to campus, if at all possible, after the appointment's over with, and then we'll be there as long as it takes to get everything done I need to do. So that's coming up this coming Friday, the 1st. Then on the 8th, I guess it is, the next Friday, I've got meetings down in Mobile and this is so ridiculous, the student in my last class said the drive time to Mobile is 4 hours, or he was saying actually less than 4. I don't know if I can make it in that time, especially if I have to stop for gas or something. But anyway, I'll probably leave home by 7. That's normally the time I get away, or soon after 7 as I can, and drive. And the meeting starts at 12 noon, and it only goes till 3, and then I turn around and drive back, and that's another at least 4 hours drive back. So that would get me 7 o'clock coming back. So that's an awful lot of driving for 3 hours of meeting, but I was told this morning that, I need to be there. I thought this is such a waste, but they said, you need to be there. So I'll be going to that on the 2nd Friday, that's the 8th. The 3rd Friday, which I think is the 15th, I've got an eye appointment, and that's right across the road here at UAB West. I thought it was going to be at Eye Foundation Hospital. I'd go to the Birmingham campus after that, but since I'll be here, I think I'll just stay here on this campus unless there's some reason to go to the Birmingham campus. So especially if I've just had my eyes dilated, which I think I will have by then the odds are I'm not going to be all that comfortable driving even with the deep shades that they give you. So I'll probably be here for a while, and then as my eyes feel better, I may head to Birmingham later. But that appointment's at 8:15. So hopefully I'll be through with that by 9:15, 9:30, something like that. So I have plenty of time in office hours after that. So 3 Fridays in a row, I'll be somewhere other than where I was supposed to normally am. And actually last Friday I wound up being on the Bessemer campus all day rather than Birmingham because I had to make up a class for when my earlier appointment, my hematology appointment, was the previous Tuesday. So anyway, that's the upcoming events, and especially on Fridays. Now, where we left off last time was in Chapter 2, First Order Differential Equations, Section 2.3, Linear Equations, and we were getting ready to start Example 7, or at least that's what I have. And we're going to be using the arrow function, which we introduced at the end of the last class. We didn't do much with it, so here we're going to do something with it. So here is it says solve the initial value problem. dy by dx, okay, dy dx, it still doesn't look like a very good d, minus 2xy is equal to 2. With the initial condition, y of 0 is equal to 1. All right. Now, just get used to going, this is why I do this. Get used to going through this mentally in your head to see what you can do. Is this equation separable? If that was not an equal to on the right, it would be. And that would be fairly straightforward and easy to solve, separable. Okay? And that would be the way to go. However, this is not separable. With that 2 over there, you can move the minus 2xy to the other side. You cannot separate the x and the y then from each other. Not with that plus 2 in it. So, not separable. So therefore, linear form is probably the best way to go. This is set up for linear form. In fact, it's standard because you don't have your coefficient for your dy dx is 1. That's exactly what you want. This is now your p of x, minus 2x, I believe it is. Let me make sure, yeah. Our general solution was always a plus px. So let me include the minus sign in that. Okay, minus 2x. P of x is minus 2x, and then your 2 is your constant at the end. What's the first thing you do once you make sure you're in standard form? We are. And identify your p of x. We did. Next thing we do is integrate that p of x. So you integrate minus 2x dx, which of course is minus 2x squared over 2, okay, which is minus x squared, okay. Don't use a plus c ever here. Don't do it at this point. Okay, there's your e to the px, okay. I'm sorry, there's your integral of px, and that's minus dx. And what do you do with that? Raise it to the eth power. So this will be e to the minus x squared. Ha! This is now gets you into your arrow function, because there's no way you can integrate e to the minus x squared. But we're not there yet. That is your mu. We've been calling it the mu, the integrating factor. Multiply that by each side. So it'll be e to the minus x squared dy dx minus 2xy e to the minus x squared. Okay, I've got the y in there. I should have put the y on the outside. Doesn't matter. Is equal to 2 e to the minus x squared. Okay. All right. Now, this side here should be, by all rights, should be a perfect derivative. Okay? Derivative of a product. D of, I'll even put d by dx of. Okay? And that should be your integrating factor times your y. E to the minus x squared times y. Okay? Now, let's check and make sure we're right on that, that is a perfect derivative. Well, it's the first times derivative of the second. Yep, that gives you the first term here. Plus the second, y, times derivative of the first, was e to the minus x squared times chain rule minus 2x. Yes, has every piece of it there. And this is equal to 2e to the minus x squared. Okay, make sure you write it right. Okay, let's write this in differential form. Take out the dx here, move it over there, is one way of looking at it. The integral of a perfect derivative is e to the minus x squared, y. And this integral here would be 2 times the integral of e to the minus x squared dx. I told you that was where it was coming. All right? Now, from our error function from the previous page, we see this is this representation that we have here. If we put, and here this is a little artificial, but if we were to do this integral here from 0 to x, that's going to reproduce exactly what we've got here. Well, not quite. If you had x, that's going to give you the same thing, but when you put a 0 in there, that's going to give a minus y. And we've got a student. Peyton's here. I'm so glad to see you. It's so boring talking to myself. So. Okay.
It's only bad when you start arguing with yourself.
What's that?
It's only bad when you start arguing with yourself.
Well, I do that periodically. So. And I always lose. So. Okay. Now, I gave a few announcements at the beginning. I don't think any of them will be particularly important to you. Do you ever have need to come up here on Friday, especially to see me? Because it's okay to come on Friday. I'm not. It's just that I'm going to be gone part or all of each of the next 3 Fridays, including this one. I've got a dermatology appointment at 9:15 this Friday, which means either I'm not going into the Birmingham campus at all, or if I go in, I have to leave after 45 minutes after getting there to go back to get the appointment. So I think I'd be a lot better off spending the hour commute there and back just working than commuting. But I got to check with my boss and see if that's okay with him. The next Friday, I'll be gone all day long. I've got meetings down in Mobile for 3 hours, and that's at least a 4-hour drive.
Yeah. Maybe
longer. So I'll probably leave by 7 in the morning. The meetings are 12 to 3. If I leave at 7, that gives me 5 hours to get lost a time or two or whatever, or find the campus or whatever. So I will be on the road from 7 in the morning, or shortly after 7 probably, and then probably not get home until about 7 that night. So a long day for a 3-hour meeting. So I won't be on campus at all that day. Then on the next Friday, that's the 15th, I believe it is, I've got a eye appointment, but I found out it's right across the road here at the UAB West Hospital. I was surprised. I thought it was going to be at Eye Foundation in Birmingham, and I would go on to Birmingham campus from there, but it's going to be here, so I get to probably just come across the road and stay here. Now, if I need to go to Birmingham, I can, but usually after those appointments, my eyes, I really don't like driving that much with the eyes dilated and stuff. It just
Oh, yeah.
is either painful or it's inconvenient, and I'm afraid it'll
interfere. Schaefer offered an option where they paid for $30. They did dilate my eyes instead of the imaging system. So they then used the picture of my retina instead. I would dilate my eyes and look in. It's really nice.
Oh.
I actually recommend because you don't have to. It's worth $30 to not have sore eyes for the rest of the day.
Right. Well, the trouble is, I think I've got a cataract that's growing, so I think they're going to have to see that better than probably. I don't know. I don't know what they. But what did you say that procedure was?
It was Schaefer Eye Center in Hoover. They had it's just like a photo machine, but you sit in front of it and it scans the green light over your eye. Takes a photo of it from the inside, so that the optometrist had to sit there and look in it, the scope, and then the optometrist can just look at the photos and see.
Interesting.
Pretty nice.
Yeah.
Didn't have to do dilation and didn't have to have sore eyes.
Right. All right. Well, anyway, I had started on example 7 on page 61, and I had gotten this far. I'll just briefly go over what we did with it. Here was the problem. dy dx minus 2xy is equal to 2. Initial value problem with y of 0 equal 1. Okay, now, I just mentioned this one's not separable. If that had been a 0 over there instead of a 2, that would be easily separable. You wouldn't have to mess with the linear form. It's not separable, so you do have to mess with the linear form. First thing you do is in standard form, yes, coefficient of your derivative is 1. Perfect, okay? We don't have to do anything there. Then identify your p of x, and that's minus 2x. Well, what do you do with that p of x? Integrate it. Integral of minus 2x is minus x squared, okay? Then, so you've got a minus x squared is your p of x. Raise that to the e power, that's the power of e. So e to the minus x squared becomes your integrating factor. And as soon as you see that, you know you've got an error function coming up here because e to the minus x squared is all over in the error function. And that's the last thing we did, so that's what we're gunning for. All right, so I keep finding these stray marks on the screen, and I think my pen drags a little bit, or I'm lazy and don't lift it high enough. Okay. So, and when you multiply that, the integrating factor by each term on both sides of the thing, you get e to the minus x squared dy dx minus, I wish I'd have written this differently, minus 2x e to the minus x squared y is equal to e to the minus x squared. Okay? This should be a perfect derivative. It is. It's the perfect derivative of your integrating factor times y, e to the minus x squared times y, because if you take a derivative of this, you get the first, e to the minus x squared times the derivative of the second, dy dx, perfect, plus y, there's your y, that's the second, times the derivative of the first. And the derivative of e to the minus x squared is e to the minus x squared times chain rule minus 2x. So we know we did that right. So we write this as a perfect derivative, d by dx of that. And then, since you know that's a perfect derivative, multiply both sides by dx, or in other words, write it in differential form, and then you have this integral. E to the minus x squared y, that's the derivative of, that's the derivative of an integral, of a perfect integral, it's going to be that, or the integral of a perfect derivative is going to be that. So that's going to be here, and then you'll have this here. Now, here comes the part where you have to interject your limits, okay? And these limits are going to go x going from 0, well, your number one, your variable x here is going from 0 to x. So you really need to change that variable e to the integral of e to the minus t squared, or something like that. But it really doesn't matter. You know the integral of a perfect derivative is the inside of that. But you have to evaluate this from 0 to x, okay? And this is the t part here. And I guess I should change that. Yeah, they do in the book too. Make this a t squared and that a t squared. And this a t squared and that a t squared. Okay. So change these all. Oops, I hit the wrong key. There we go. Okay. That's t, this is a t, that's a t, and this is a t. Okay. Oh, he decided to leave work on time today. Okay. Did you have any problems?
Not today, no. Not from the other day either.
Oh, okay, good. Yeah, I was hoping it would be. And by the way, if I'm changing the variables there, I also needed to change them here too. Okay. Now, sorry, I'm going to be repeating again. Just told you about the Alabama A&M having the North Scholarship Program. You should have gotten the email. You can check, click on the link, find out all the information about it if you want to know that, and follow it up, apply whatever you want to do, ignore it, whatever. Okay. But the other announcement I had today is looking into the future a little bit. And I've not had either one of you come by, I don't think, on a Friday yet, have you? And you're not likely to? Okay. Because the next 3 Fridays, I've got 2 doctor's appointments around one trip out of town. So the doctor's appointment, I will definitely be there, let's say from 10:45 to 11 next Friday. Might be there from 8 to 8:45, but that's an awfully short time to make a trip there and turn around and go back. So I'm thinking I'm just going to go work from home and go to the doctor's appointment straight from home and then go to campus. Okay, that's next Friday. The following Friday, I'm going to Mobile for a 3-hour meeting. So I have to drive, 4 hours. Probably allow myself 5 just in order to find the place when I get down there. And maybe have to stop for gas or a break or whatever. So 5-hour drive down, 3-hour meeting, 5-hour drive back, or 4 or 5-hour drive back. It just doesn't seem worth it. Was putting off even asking if I had to go until this morning. I said, yeah, I better find out. And they said, yeah, you need to go. So I'm going to be there. That's the 8th. And then on the 15th, I've got an eye appointment right across the road here at UAB West. I thought it was going to be downtown in the, or south side at the Eye Foundation Hospital. They said, no, he's going to be at UAB West. I said, that's right across from work. So I'll come to work, walk across it. It's at 8:15. So I don't know how long it will take, but I'll probably come back here unless I have to go to the Birmingham campus. Then I'll go there. But I just as soon come here because I don't like driving when my eyes have been messed up like that. But you can get those dark shades and it's okay, but it's just not comfortable. So anyway, next 3 Fridays. And after that, I think it's almost spring break time. So I'll be here that Friday right before spring break, and I should be on campus all day that day. All right. So we were doing example 7, which is on page 61 in linear equations 2.3, first order differential equations. I'll go through this as quickly as possible. I've been through it. This is my 3rd time now. One before Peyton got here, one Sissy got here, and now one with you. So here's the problem. dy dx minus 2xy is equal to 2. Initial condition, y of 0 is equal to 1. Okay, now, if that 2 had been a 0, this would have been separable. And that would have been the easy way to go. Okay? However, the 2 is there. If you were to add that to both sides, there's no way you can separate the x and y anymore. When it's 2xy plus 2, that's not separable anymore. That was a 0. You put 2xy, yeah, divide by y and multiply by dx. Yeah, piece of cake. But this is not, so we have to do linear. Okay? Well, this is in standard form. Coefficient of the derivative is 1, exactly like what we want. Then your p of x is this minus 2x. Okay? Minus 2x. P of x times y equals f of x. And that's just a real simple f of x. Okay, well what you do once you've identified p of x, you integrate it. So you integrate minus 2x dx, and that would be a minus, well that just comes out minus x squared. Okay? Don't ever add a plus c to that integration. Don't. Just get the simple derivative, straightforward derivative. Okay? Then what you do with that p of x, you raise that as the power for e. So you put an e under here. And then you multiply everything on both sides of your equation by e to the minus x squared. As soon as you see this, you know it's an error function coming up, because at the end of the class last time, we did the integral of this thing comes out being having to do with the error function. Okay, so we knew that was coming. Okay, but if you multiply everything on all three on both sides of the equation, all three terms by e to the minus x squared, which is your integrating factor, then this turns out being a perfect derivative. Now, I didn't write it in quite the best form. It's derivative of e to the, now I changed from the x squared to a t squared everywhere, and there's a reason for that, what we're going to do next. So, in fact, I hadn't changed before, I just had changed it before you came in. Well, let's see, is this a perfect derivative? E to the minus x squared, imagine that's an x for now, times y. Well, derivative of that would be the first times derivative of the second. Yes, that's a perfect derivative. That's the product rule. Plus the second, there's your y, and this is what I wish I had written in a different order, time derivative of this. Imagine an x there. That would be e to the minus x squared. There that is. The y was there from here. And then derivative chain rule, your favorite, minus the derivative of minus x squared is minus 2x. Okay? So yeah, that is a perfect derivative. So therefore, we can integrate that perfect derivative. Okay. Here's where the rub comes in. Why we have to change from an x to a t? Because in this integral, we're going to integrate it from 0 to x to get back to x. Okay? And that seems like it's cutting off your nose to spite your face or something. But that's going to make this the error function. 0 to x. Okay? And that's why we had to change, because you can't have the integrating variable being the same as the limit variable. Okay. Now, here's where the rub comes. If you're integrating a perfect derivative, it comes out to be that. But if you're integrating within limits, you have to evaluate this between 0 and x. Well, evaluating this at 0, at x is a piece of cake. E to the minus x squared y. Yes, that's exactly what we've got here, so I'll write that down. E to the minus x squared y. That's when you plug in the x. But then when you plug in the 0 for t, e to the 0 is 1. So you have a minus y here that we wouldn't have otherwise had to mess with. Okay? But that may not be a bad thing. And we'll see if it is or not. Okay? So that's what you got on the left-hand side. If you hadn't have put the x to 0, you just would have had that one term. But now we got it, and we're back in x now. And what we've got on the right-hand side is 2 times this function here, and that's awfully close to being the error function. Okay? The integral from 0 to x of e to the minus t squared dt is going to be root pi over 2 times the error function. Okay? If you look on the page before, you'll see that. Moving that over. Well, root pi over 2, this 2 will cancel out that one. So basically, we have this is equal to, don't have much room, so I'm going to write it way over here, root pi times ERF of x, the error function of x. Okay. Now, they've done it some strange way here. I can't quite figure out why they have done it this way. They left it as an integral. And then what we're going to do here is factor out, let's see, and maybe I spoke too soon. I guess we don't know necessarily what the error function is. I don't think they gave us any limits on it, though we could look it up. But in order to avoid that and have to mark Muhammad here, let's go back and leave this off for now. Sorry. Okay. We'll leave this integral here. I'll write it back down. Okay, I almost hit the wrong key here. Leave that in there and take this out, because everything we did was right, but we maybe did it too soon. So this thing is equal to that. Okay? Now, I'm running out of room down there, so let me write it up here. E to the minus x squared y minus y is equal to 2 times the integral from 0 to x of e to the minus t squared dt. Okay? Now what they suggest is now plug in y is equal to 0, y of 0 is equal to 1. So in other words, when x is 0, y is 1. Okay? So, let's plug in a 0 for x and a 1 for y. A 0 for x here is going to give you e to the minus 0, which is going to be 1, and y is going to be 1, so this will be a 1 minus, and y is equal to 1, so that'll be 1 minus 1. That 0 is equal to 2, and here the integral from x to 0 is 0 to 0 is 0. So this isn't getting us anywhere. Well, what they did here, I'm sorry, and this is, okay, let's back off a moment here. Okay. I think I had it right. Sorry, I could have left it. No. Sorry. They're only plugging in the y of 0 is equal, okay. Yeah. X, remember, is the t. T is the integrating variable. That's what we're plugging in for. The x stays x. So, sorry. and when x is 0, y is 1. Okay? So we can plug that in here, and we indeed get 1 minus, it's still coming out that way. No, we're not plugging in for 0. We're only plugging in the 0 in for the y of x. That's the part that's bizarre here. Okay. And y of, so this one, this is the first term here, plugging in the x. That gives us e to the minus x squared y. If it'll write, there it comes. Minus y, and then when we plug in 0 for this thing, this gives us y of 0. Okay? Because y is a function of x. So this, on this one is x, and on the second one is 0, because that's what you're plugging in. And this is what's equal to your 2 times the integral of 0 to x, because we haven't evaluated that one yet. This is part of pain in it. E to the minus t squared dt. I don't know why the pen's not writing well. But this is a 1. Y of 0 is 1. So what we have now is e to the minus x squared times y minus 1 is equal to 2 times the integral of 0 to x e to the minus t squared dt. Okay. No. Yeah, that's right. No. So now we add 1 to both sides. E to the minus x squared y is equal to 1 minus 2 integral 0 to x e to the minus x squared dt. Okay. Whew. Now we're going to isolate the y. So multiply everything by e to the x squared. Because e to the x squared times e to the minus x squared is 1 over 1. It's just 1. So we'll multiply everything by that. So those give you y is equal to e to the x squared minus 2 multiply. You could be dividing by e to the minus x squared. That would work, which is same as multiplying by e to the positive x squared. Right? Okay. So this would be e to the x squared times the integral from 0 to x of e to the minus t squared dt. Sorry, I wrote x in here. That should have been a t. I think I said t and wrote x. Okay. Anyway, all right. This is plugging in your thing. Now, I'm sorry? Okay, one more time.
I thought it was going to be negative 1, because 1 minus 2 gives you negative 1, not 2.
Okay. What? Oh, that's a plus. Is what you said. Yeah, I'm sorry. I don't know how that became a minus, but yeah, you're adding 1 to both sides. Yeah, is that what you're saying?
So when you add 1 to both sides, wouldn't that make it 3 then?
No, it's not 1 plus 1. It's 1 plus 2 times this integral. It's not 1 plus 2 times the integral. It's 1 plus 2 times the integral.
I see what you're saying, because you're handling 2 as if it's a constant. That's why.
Okay, but the constant is the coefficient of that.
Yeah.
So it's like if that was a 3z on the right-hand side, you do a 1 plus 3z. You wouldn't do a 3z, you know. Right.
I got you.
Yeah. Okay. Now, where this leaves us is this thing looks a lot like the error function. Okay? If you had, and again, the way they do it, judiciously multiplied this by a root pi and divided by root pi. So had a root pi here and a 1 over root pi here. We haven't changed the value any. It's just multiplied by 1. But now 2 over root pi times this thing here is the error function. Same as what I was getting to earlier, but I was plugging in too soon. Okay, that's the error function. Now, the other thing they did, they factored out the e to the x squared from both sides. So I need some more room to write. So let me go up here and erase some stuff that we've already used, and hopefully we won't need it again. I don't know why my eraser's not working. Okay, I hope I'm not erasing too much. But we've already passed this stage, so I have such a small screen, I can't get everything on the problem in at the same time, but you can write as much as you want to on a piece of paper. I'm going to get rid of this too, just because it's fouling up the appearance here. Alright, that took a while to erase. Okay, so what we have here is y is equal to e to the 2x, they're factoring out of it because both of the, no, I'm sorry, e to the x squared. Goodness, where's the brain today? But this is the positive x squared here, okay? Factoring that out of both of those two terms, and that leaves us 1 plus, okay, root pi that we multiplied in there, times, and this thing here was the error function, ERF of x. Now that's our solution with the thing written in here, okay? 1 plus e to the x squared, no, sorry, y is equal to e to the x squared times 1 plus the root pi times the error function. Now, you have to have a package that can write the error function before you can evaluate it, because, and I can't, I mean, I don't have those tables in my head or anything. So they said using CAS, which is computer algebra system, this is what it looks like. And sure enough, it goes to the point 0, 1. This is what the error function is looking like there. Okay. Now, it says C problems 43 to 48. I have a feeling that means we really don't want to see those, but they say to see them anyway. So if you want to do some more work with that, I can almost say I'm not going to ask you any question that's really going to require much to do with it, because the error function is one you can't integrate. We just give it a name so we don't have to write it down all the time. But someone has gone through and created tables of it, excuse me, or computer programs to calculate it. But there's no way to do it without that. Okay. And then there's a little blurb on the use of Mathematica or Maple to these are two computer algebra systems that you could use. And they give you some hints on how to do it. And since we don't have any, those are fairly worthless hints. Now, the remarks, most of the time these turn out being more of a pain in the neck than they're worth. But this is perhaps important for later. Anyone need this one up there a little longer? Not a particularly great and instructive problem, but it's just how you use the error function if you ever need to. You have that integral you can't integrate and get it into the form of the error function, and then use some package that has those calculations in it. All right. Now, here's something that seems, again, I think to a pure mathematician, like it's a trick, a dirty trick at that. Okay? Here's a differential equation. dy dx is equal to 1 over x plus y squared. Now, that's number one, not separable. And number two, not even linear. Okay? So nothing we have in our tool belt now can even come close to that. Okay? And here's the dirty trick. Seems like an okay thing to do, but on the other hand, it seems like a dirty trick. Because remember, dy dx is not a fraction, it's an operator. But they say, believe it or not, the reciprocal is doable. Well, you're not supposed to be able to do this, but they do. Dx dy, dx dy is x squared, x plus y squared. I can't write either. Okay. Now, if you look at that, you say, but wait a minute, that's not linear either because y is squared. But notice y is not your independent variable your dependent variable anymore. X is the dependent, y is the independent, and now that's perfectly okay. This is linear in x. That was not linear in anything, much less y. Okay? But this is now linear in x because x is your independent variable now, y is your dependent variable. So you can write this as I'm sorry, I'm so used to writing dy dx. One more time. Dx dy, it just doesn't seem right, okay. Minus x is equal to y squared. Remember, on the other side, that can be any function at all. It doesn't have to be linear or anything else. So this function is linear in x, not linear in y. Okay? And then you can go to town with that. And by the way, it's still not separable. You can't separate it, but you can use the linear form as long as x is a function of y. Okay? Not y is a function of x. So now you do a p of y, not p of x, and you integrate that dy, and you carry that on through. And it's just like any of the others. Okay? They don't solve it for you. They just say, ha, there it is. Okay? And actually they do a little bit. Okay, so let's do it. Your p of x, once you've written it in linear form, your p of y now is minus 1. Okay? Not p of x, p of y is minus 1. And you integrate that, okay, with no constants or anything, and this gives you minus y. Okay? And then this is your integral of p of y. Then you raise that to the e, and that becomes your integrating factor. So now you do that integrating factor, e to the minus y times dx dy minus e to the minus y x is equal to e to the minus y. So I'm going to put the y squared in front just because it's a little easier to write that way. Now this should be a perfect derivative, right? Let's see if it is. Now it's d by dy now, not x. It's hard to write, but it's d by dy. Hard to say too. Let's see if it is. I'm sorry. Yeah. Okay. No. I'm sorry. I wrote that wrong. It should be a perfect derivative, and the perfect derivative should be, this is where we put the d by dy, of the integrating factor, e to the minus y, times the x, your dependent variable. Okay? Well, let's see if that is indeed a perfect derivative. It'd be first times derivative of the second, perfect, plus the first, second times derivative of the first. Derivative of the first is e to the minus y, chain rule times the minus. Yes, that is. So this thing here is a perfect derivative. This is y squared e to the minus y over here. Okay? So you write that in differential form, integrate, and what you have now is e to the minus y, I'm going to put the x in front, I just don't like having it in back, is equal to, and you're integrating this. Well, that's everything's in terms of y, which is just what you want. Unfortunately, that's going to be a, remember how to do this one? Does that ring a bell? Integration by parts, because it's a product, and one of these will get simpler when you take the derivative, the other doesn't get much more complicated when you integrate. Let u dv. Okay, that's going to be let u be y squared, dv be e to the minus y dy. Let me carry that on further. And they do actually give an answer, so let's do that. I hadn't planned to do this, but let's do it. This will be, this is integration by parts, let u equal y squared, and dv equal e to the minus y dy. Okay, you always have the d's with each other. You differentiate this, du is equal to 2y dy, and you integrate this one, and that would give you v is equal to antiderivative of e to the minus y would be e to the minus y, but with a minus sign in front. And if you're not certain of that, take a derivative of it. The derivative of this would be minus e to the minus y, change rule times the minus 1. So yeah, that's about perfect. Now, what that integral becomes then is u times v, which is y squared minus y squared e to the minus y, the minus came from the v part down there, minus the bottom line here, okay, and since you already have a minus, minus times minus will be plus the integral of this bottom line, which would be e to the minus y times 2y, let me put the y in front, dy. Well, the bad news there is you got to integrate by parts again. But at least this is simpler than that one was, because now your u can be y, and you're going to finally be rid of it, but you're going to have another term there. So you do this again. Let u equal y, this is a different u, of course, and same as before, dv equal e to the minus y dy. Yuck, that's running into the edge. Then du is equal to dy. We finally will be able to get rid of the y. And your v is equal to, just like before, minus e to the minus y. Okay, because if you took a derivative of that, you get e to minus the minus y times the minus 1. So, yeah. So, this one becomes, don't forget this, the minus y squared e to the minus y is there from before, plus 2 times the integral, plus 2 times the integral, sorry, don't write the integral yet. That integral, yuck! Yeah, it erased. Okay, plus 2 times this integral is u times v. This is driving me nuts. U times v. My pen never came back. Okay. U times v, which is, this 2 is times in front of everything here, minus y e to the minus y, the product of those two. And I'm going to put the minus in here, and I'll change it in a minute, the bottom line here. And that minus is going to make that a plus then. So I said I would change it. Didn't take long. The integral of e to the minus y dy. Finally, we can integrate that to be minus e to the minus y. Okay. So, and I'll close out the bracket here. So what we have, the right-hand side here, this was the left-hand side. The right-hand side is going to be, I'll rewrite it here, x e to the minus y is equal to minus y squared e to the minus y plus 2, no, minus 2 y e to the minus y, and then a minus here because it's going to be a 2 because that 2 multiplies by antiderivative e to the minus y is minus e to the minus y plus c. Okay, finally. All right. And then to get this x, remember the independent is a dependent variable, so get all your y's on the other side multiplied by e to the y, right? Which will leave us x as a function of y is equal to, well, this will wipe out that, it'll wipe out that, it'll wipe out that, okay? And you'll have minus y squared minus 2y minus 2 plus c to the e to the y, because you had to multiply that term by 2. And that's your solution that they show here. Minus y squared minus 2y minus 2 plus c e to the y. Okay. Now, this expression is then an implicit solution to the first equation. Okay? Because no way you can separate the y's here, but you got the x separated, but the y. So our first equation here, no, you can't do it, except there's its solution with that y. If you could isolate the y, that would be a solution in x. Of course, you can't, so that implicit solution, which somehow is not very satisfying, but it's okay. It's there. Now, it says here mathematicians have adopted their own certain words for engineering, from engineering, which they found appropriately descriptive. The word transient used earlier was one of those terms. In the future, the words input and output will occasionally pop up. The function in F in 2, which is right back at the beginning of the section, is called the input function. That's the part that's to the right. Make sure. 2 at the very beginning of the section here. The f of x is to the right there. That's the input function, or the driving function. The solution y of that will be the output function, or the response. Okay? Ignoring the stuff in between. The p of x, that's not there. Your answer y of x will be the response. Okay? Now, there's another place we use the term specific functions with error function, also applies to the sine integral function and the Fresnel sine integral function, which, as far as I'm concerned, unless you're going to be in a very specialized field, I don't think you'll ever see. So I just assume not ever see them. But depending on what you're going into, you might run into them. I don't know.
How specialized are you talking?
What's that?
How specialized would you see something like that?
In what?
How specialized of a degree would you start seeing?
I don't even know. It may be only in pure mathematics. I don't know if there's an engineering field that uses these. I'm just not at all. I've seen them, and I see them written out, and I can't for the life of me guess who would ever use those, except it's just a sort of an abstract algebra type thing. And it may be that's the only place it's ever used. But anyway, that does finish 2.3. So homework exercises here, and I've given these before. any of the odds that are in the back of the book 1 to 23, and any of the odds that are in the back of the book 25 to 35, and then any of the odds in the back of the book that are either 37 or 39. If 41's in the back of the book, try that. 43, if that's in the back of the book, try that. 45, if that's in the back, try that. And then 47 gives you that sine integral function that they talked about here in the remarks at the very end of the chapter. And that's one of these functions that you will not ever find in a table that you can do. Okay? And they give you an example here of a differential equation that you would wind up using that sine integral function. I don't know if this is just a made-up differential equation that you would ever find anywhere in real life. If you did, then there is a purpose for it. Okay. Then 48 gives the fractional sine integral function, which looks somewhat, not really at all very similar, but it gives you another function. I'm not suggesting you do either of those unless you just have an interest in them. Certainly not 48, because that answer won't be in the back. The discussion problems, generally none of those are in the back, so only do those if you have a special interest to do so. But by the way, if you can find an application for an error function, inverse error function, no, that's not what they call it, complementary error function, sine integral function, or fractional sine integral function, those could be some good paper topics, you know. Where do you ever use these things? Where are they appropriate? If you want to follow that up, you certainly can. That's completely up to you. Okay. All right. Let's move on to 2.4. Any questions? 2.3? All right. 2.4. Exact equations. I found that an unusual name, but I guess it's descriptive to a mathematician. I don't know. Here is an example of a simple first-order differential equation. Y dy plus x y dx. I knew something seemed bizarre about that. Y dx plus x dy is equal to 0. Okay? Now, that's separable. It's also linear. Okay? And although it is both of those, and you could solve them very simply by separation of variables, maybe not quite so simply by linear, but it would be okay, there is another way to do it. In the alternative manner, by recognizing that the expression on the left-hand side of the equality is a differential function of f of xy is equal to xy. The f of x comma y is equal to xy. Why? Okay. What if you took a derivative of this? Okay. Now, d of xy, okay, in differential form. That would be, hiccups, that's a product function, so it would be x dy plus y dx. That's real simply written product function in differential form, okay? And it's saying that this is 0. In other words, the product of these is a constant, because its derivative is 0. Okay. Now, That's a very simple form. Here's one that's a little less simple. If you had m of x and y as your dx, coefficient of dx, plus n as a function of x and or y or both, dy is equal to 0. Now notice in both cases here, so far, we've had them equal to 0. Okay? And I think there's a reason for that, because just like before, we saw that that meant that derivative, if you can come up with a function that will work with, if its derivative is 0, then you know that's going to be a constant. Okay? And I believe that every one of these up to a point is going to be equal to 0. So these exact equations, that's going to be the key. They're going to be equal to 0. No matter what this coefficient function of x and y is, no matter what this coefficient function of x and y is, that part's got to be a 0. Okay? Now, the techniques that we're going to show here will work if these are exact equations. All right. Now,
It's time.
oh, it is time, isn't it? Okay. So we'll pick up from there next time. Let me find the pencil here. We're basically at the top of page 65. So we just barely got started here. And even though it might look or smell like this might be a little complicated, you'll find these are not that bad to do. Okay? That sounds real promising, doesn't it? Okay. Not that bad to do. Okay.
Yeah, not encouraging.
Yeah. But at first, those linear, they think, oh, wait, you integrate, then you raise it to an exponent, and then you do this, you do that. But after a while, after doing a few of them, you say, oh, okay, yeah, these just follow this routine. Well, there's going to be a routine in this one, which frankly, I find, at least to begin with, easier. But then there's a place that we get to, what if you have an inexact, can you make it exact? Now that's where it gets a little more complicated. That's going to be the second part of this section. But this part, the first part, I think you'll find it's okay. Yeah. All right, we'll end it there today. I'm hitting the wrong key. Okay, that's all.